We're going to start this unit off by graphing functions, the sine function and the cosine function. Now the last unit, we calculated values for specific angles around the unit circle. And the first part of this unit, we're going to treat sine and cosine as functions with an input and an output, and we're going to graph their value along the xy axis. So the angle measure would be our x values, and the value of the function is going to be our y value. So we're going to start off with the table of values for the sine, and we have all of our angle measurements in degree measure. We're going to write in the corresponding radian measure. So what I recommend is you do this first, because you got to memorize these anyway, and we will fill out this table and then talk about the corresponding value of the function for each radian measure. So here we have all of our corresponding radian measures in terms of pi. For 45 it's pi over 4, 90 degrees pi over 2, etc., etc., etc. So for each one we're going to write a decimal value for the sine of x. And so here we go, I guess. For the sine of 0, we talked about that. That's a quadrantial angle. The sine of 0 is 0. For pi over 4, it is 0.707. At pi over 2, the sine is 1. 3 pi over 4 is the second quadrant. Sine is still positive, so it's 0.707 again. Reference angle is 45 degrees. At pi, 180 degrees, the sine is 0. And then in the third quadrant, sine is negative. 3 pi over 2, it's negative 1. And in the fourth quadrant, the sine is negative. And then we're back to 0 again. So what we're going to do is graph this function, and if you look at your values, the min and max are basically positive and negative 1. So I'm going to scale my graph just so it's a little bit bigger, and I'm going to put positive 1 here and negative 1 there, because I know it doesn't get any larger or smaller than those values. Now my x-axis, I'm going to mark off in pi over 4. So every 2 units is going to be pi over 4. And to keep my graph from getting too cluttered, I'm going to label every other one. So there's pi over 2, and that's pi. It's important that you scale your graph appropriately. A lot of times kids don't scale the graph, and you lose a lot of points that way if you don't put a scale on here. Okay, so there's my scale. And what I'm going to do is just plot these points. So I got 0, 0. We start at the origin. And then at pi over 4, 2, 4, 6, 8. Oh, this is like 25, 5.25. So we're right about just underneath that little tick mark. So it's going to be right there. And then at pi over 2, I'm at 1, and then we're here again, and then here, and then we reverse the other side, right about there. And remember, we don't want to create straight lines. We're going to sketch in as smooth a curve as we can, and you can probably do this better on your sheet than I can on my iPad. But there is a general curve for the sine function. If I don't restrict the domain, then I should probably put arrows here. And if you look at the domain, like I just said, I didn't restrict it, so the domain is all reals, but my range is limited. I only go between negative 1 inclusive and positive 1 inclusive. If I wrote that in interval notation, it would be negative 1, 1. So we're going to do the same thing with the cosine curve, and again I've input all my radian measures here for the corresponding degree measure. So here we go. The cosine of 0 is 1, and then at pi over 4 it's the same as the sine, it's 0.707. At pi over 2 it's 0. At 3 pi over 4 we are now negative for cosine because it's the second quadrant. At 180, it's negative 1, and then we're negative again in the third quadrant. 0, and then we go positive, and we're back at 1 again. And again, I'm going to scale my graph the same way. So here we have our same scale as last time as far as the x and y axis goes. And so we're going to graph some of these points the same as we did with the sine curve. So at 0 for the cosine, I start up at positive 1. At 45, I drop down just a little bit to the 0.707. And then at pi over 2, I'm at 0. 3 pi over 4, I'm at the negative 0.707. At pi, I'm at negative 1. And then we start to increase again. Here and here. So if I do my best to draw a smooth curve, he looks like that. And the domain, once again, just like for the sine curve, it's all reals, and the range, again, goes from negative 1 to 1 inclusive. So I could write it like that, or I could write it like this. And if you look at the two graphs, you can see both of them on your paper. If you look at them, they really are the same graph, just one happens to be shifted from the other. So if you think about that, they have similar values just in different locations if you look at the table of values. Now, these functions are called periodic functions, and you can see why. After a certain period of time or angle measure, they start to repeat again. So that's how we define periodic functions. Here's a more formal definition for you. Periodic functions are ones where the y values repeat after every certain period of x. So if you look at sine of x and cosine of x, if I follow the cosine function here, I start up at positive 1, and then I decrease it, and I increase again, and I'm back up at positive 1, and the cycle repeats. So the period length is going to be 2 pi. And that's going to be the same for the sine function as well, because the only thing that's different is where the maxes and mins are showing up. But the actual period length itself for both of these functions is 2 pi. The next thing we're going to define is what we call the midline of a function, and that helps us figure out the min and max. So the midline is the horizontal line that divides the function in half. For the standard function, it's going to be the x-axis. So whether it's a sine or a cosine, that's that middle line there. But we could have a midline shift, and we'll see those later on, where the midline doesn't have to be the x-axis. My function could be centered somewhere else. But the midline is the value that cuts that function in half horizontally. The next thing we're going to define is the amplitude of a function. So the amplitude is the distance between the midline and the maximum value. So it's halfway to max, or from the halfway point up to the maximum. Now what you have to remember about the amplitude is that it is always positive. We don't have a negative amplitude. An amplitude is like a dilation, where we are vertically stretching our function. And we know when dilations are always considered positive. So for our standard function, if it has a midline around the x-axis, it's pretty easy to read the amplitude. The amplitude is going to be that distance here from the x value up. But if we have some other kind of shift, and let's say our midline is down here, the amplitude is still going to be positive even though our values are negative. The amplitude is still going to be from here to the maximum. So it's the difference between the two values which still makes it positive. Alright, so let's compare the graph of the regular sine curve to the graphs of 2 sine and 0.5 sine. So think to yourself, how is that going to affect the original graph? Well, let's start off by scaling our axes. So here we have our scaled axes, and we have the standard sine curve here. It starts in the center, it goes up to increases to 1 at pi over 2, center at pi, negative 1 at 3 pi over 2, then back to 2 pi again. If I'm going to graph 2 sine of t, basically what happens is only the amplitude changes. The 2 acts as a dilation, So your y values are doubled. Anything on the x-axis stays on the x-axis, and anything else is doubled in length. So instead of being at +1, we're going to be up at +2. We're going to graph this one. I graph this one in red, so I got a point there. And I'm on the axis. I stay on the axis and back again. So it's up, down, and up. So it's basically going to be double the amplitude. If it's 0.5, again, that acts as a dilation, and we're going to chop our y values in half. So this time I'm going to have a very narrow graph. I'm only going to go up to 1/2, and then cut through 0 again, and down to 1/2 and cut through 0. How are the graphs similar? Well, you look at it and figure it out, and how are they different? And we can talk about that in class. And finally, we're going to talk about midline shifts. That's what your book refers to, the vertical shift, when we move the midline up or down. It's kind of like when we move the horizontal asymptote for an exponential function up or down. This is adding or subtracting a constant term outside of the function itself. And that basically shifts the midline up or down by a value of k. So when it is positive, we're shifting up. When it's negative, we're shifting down because it's a direct read. So we're going to end by sketching this graph. We know the general shape of the sine function. Our amplitude is 2, so we'll go up 2 units above the midline and down 2 units below the midline. And we have a midline of 3. In this case, I'm going to use 1 unit for each scale because I don't think I have enough room to scale it any different than that. Alright, so I've scaled my grid here, and since I have a +3 out here, that's a shift of 3 up, so I'm going to put in my midline. I'll make that a pretty purple. There's my midline. Everything is going to be graphed around that. That's going to be the center of my sine function. And now, since I have an amplitude of 2, my maximum is going to be 2 above the midline. I have a max at pi/2, so I'm going to be 2 above the midline there, and I'm going to be 2 below the midline at 3 pi/2. And the rest of the graph is the same. I start at 0, I'm on the midline at 0, I cross the midline at pi, and then I'm down here at 3 pi/2, and I come back up to the midline again at 2 pi. So that's a brief introduction of the sine and cosine curve, including midline shifts and amplitude.